section 7.1, we are going to take a look at some topics that we've already discussed in fairly great detail, but we're going to look at them, revisit them one more time here. We're going to start with the velocity function, 6 sine of 3t on the interval 0 to pi over 2. And we're going to ask some questions about this. We're going to look at some relationships between velocity and acceleration and position, also change in position, which is displacement, and also total distance travel given a velocity function. So far we've talked quite a bit about an integral as an accumulator, and we know that in a velocity sense, if we were to take a look at this picture, 6 sine of 3t, and we have some kind of shape like this, etc. Ultimately, as we go from left to right, we're accumulating area under this curve, and keeping in mind that if this is in meters per second versus seconds, then we're getting meters per second times seconds as our areas of each of these rectangles. When we add them all up, we get total meters. So keep in mind that, as we've discussed in the past, that if we have a positive valued function, that accumulated amount of meters is going to be our total distance traveled. Now, the issue that we come up with, though, is that if we have something like that, where we have area beneath the curve as well, when we accumulate this positive distance and then we accumulate this negative distance, those two ultimately are going to cancel each other out, this one being a little bit bigger, so it actually be a final answer of negative. And so keep in mind that that's not going to give us our total distance traveled, because we're going to take our positive direction distance and our negative direction distance, and we're going to add them together and get something ultimately negative here in this case. Okay, what it does, though, for us is it does give us displacement. This is going to be our change in position. So if we knew our initial position was, let's say, 5, for instance, so we see x of 0 is 5, and we knew the value of this integral right here was, just say for argument's sake, negative 2, then our, and say that that's time 5, if you will, then our x of 5 is going to be, our new position can be found by taking our original position, which is 5, and then adding our displacement. Okay, we have negative 2, so ultimately we're 2 in the negative direction, so that means our position at 5 would be 3, of course. And again, in this particular case, for argument's sake, if we had an initial position of 5 and we accumulated, let's say another 5, then our final position there would be 10 in that case. So let's go back up to the sine function again and answer a couple of questions regarding this particular velocity equation. One question that we're going to need to ask here is determine when the particle is moving to the right or to the left or stopped. So we know that, again, given this is our velocity equation, that the motion in terms of left and right is going to be determined by the value of the velocity. The sign on the velocity, if it's positive sign, it's going to be moving in the positive direction. If it's negative, it's going to be in the negative direction. And when the velocity is 0, of course, it would be stopped. So the issue here is then can we find points here on this interval, 0 to pi over 2 they gave us, so that we have the velocity equaling 0. So keep in mind that if we set that equal to 0, 6 sine t, or 6 sine of 3t, that is, equals 0, can we find a value that will give us 0? Well, we know that that at 0 itself, we know that that's going to be a candidate, because if time was equal to 0, we'd have 0. We also know that we're going to have sine becomes 0 again at pi. So keeping in mind to have pi here, the question is, what would the t have to be to give us pi? Well, ultimately, if we want 3t to be equal to pi, then we could divide and get pi over 3. So time pi over 3 is going to be another candidate. And we know that there's really an infinite amount of candidates here, except for the fact that we're on a closed interval 0 to pi over 2. So therefore, if we go any further than that, the next time we'd have it be 0 would be at 2 pi. And if we divided here, we get 2 pi over 3, which is out of the range here, or the domain, I should say. So that means that we don't need to worry about that one. So 0 and pi over 3 are candidates, one being an endpoint, one being somewhere in the interior of the interval. And then if we do our first derivative test here with our velocity, put our 0 and our pi over 3 on here, and I would also put the pi over 2 on there, even though it's not a candidate. It is an endpoint, so it essentially is a candidate, I suppose. And let's see what's going on between these two. So if I do something between 0 and pi over 3, like say pi over 6, for instance, pi over 6 in here would give me pi over 2, 3 pi over 6, pi over 2. So that would be 1. 6 times 1, of course, is 6, so we'd have positive there. And then if I pick something between pi over 3 and pi over 2, and ultimately we could come up with whatever fraction it may be that we can choose, it's going to end up being negative, and so therefore we're going to have a change here between positive and negative for our derivative. And ultimately, to answer the question, again, the question is determine when the particle is moving to the right, so we'd say it's moving to the right on 0 to pi over 3, and it's moving to the left on pi over 3 to pi over 2. And remember, in terms of using brackets or parentheses here, we can use either. It really doesn't matter. So we'll just go with parentheses for this time. For the time being, actually, I'll go with brackets for the endpoints. And then the stopped part is, of course, going to be when the velocity equals 0, which is going to be at pi over 3. Right? Now, technically, since the 0 is also a candidate, and it's also a part of the interval, since we're including it, we'd say it's stopped at pi over 3 and 0. Alright, so the next part here is we want to calculate the particle's displacement over this given time interval. Now keep in mind that the situation we can see is going to be something like this because we have positive and negative velocity values. And so therefore our displacement is always going to be just the integral over that time frame. So the displacement is always going to be the integral from a to b of v of t dt. So in our case, we're going from 0 to pi over 2, 6 sine 3t dt, and we're just going to go ahead and calculate that. And we can, of course, use the fundamental theorem because this is something that's fairly easy to integrate, but for time's sake, we'll type it in the calculator and see what we get. So ultimately the answer is 2. So that would be our displacement. So I'll keep that in mind. And so that means if we knew an initial position, we could add that displacement to the initial position and get our final position at pi over 2. If we do that, we don't know the initial position here, but we can calculate the displacement nonetheless. And then the other question is total distance. And total distance, remember, is going to be whatever we go in the positive direction plus whatever we go in the negative direction. And that's going to be total distance traveled. And again, think of it like this. If I were to drive from Kennewick Hills to my house, and I went all the way to my house and then all the way back, my displacement would be essentially 0 because I am in the same position that I started. But that would definitely not be my total distance because ultimately I traveled to my house, which we'll call a positive direction, say it's 3 miles, and then I drove back to Kennewick Hills, which ultimately would qualify as a negative 3 miles. And if that's the case, then again my displacement would be 0. Okay? However, my total distance traveled, I would want to make my negative distance positive and add those two together to get the total distance traveled. Because again, if I drive to my house and back, I didn't go no miles. I went 6 miles ultimately. I went 3 there and 3 back. So to remedy that, then for our integral, we would just use our absolute value. So that would make the negative areas positive and ultimately give us our desired result, which is total distance. So we do our plug in our absolute value here of our integrand, and we hit enter, we will get 6 ultimately, and so therefore our total distance traveled will be 6, which ultimately means that remember we looked at earlier, we had that split point of pi over 3. There it was more positive than negative, or it was positive for longer than it was negative, so it shouldn't be terribly surprising that the positive part here must have been in order to give us a displacement of 6, our total distance traveled, or our total distance traveled is 6, our displacement being 2. Alright, so that means ultimately where there was more positive area than negative area, ultimately 2 more units of positive area than negative area. Okay, so ultimately that's our work with total distance and displacement, and also working with the motion in terms of the direction. Again, velocity being positive means a positive direction, negative means a negative direction. Now, the other things that we've had discussions about as well is in general just the integral as an accumulator, and the title of this section is called integral as net change, and ultimately that's the same thing that we're talking about when we say integral as an accumulator. So I want you to take a look at example 5 that's on your page 368, and there's a problem here regarding potato consumption. And what I want to discuss here is that when we have this situation, it says from 1970 to 1980, you got the rate of potato consumption. This is kind of the giveaway here that we're dealing with a rate function. So the COT function we're given is given in millions of bushels per year, T being years. And the question is how many bushels were consumed. Well, we've discussed already when we have such a function, whatever it may look like, if it's in millions of bushels per year, which again is clearly a rate function versus years. If we find the area under the curve, if we were to find a rectangle area, we could have bushels per year times years, which ultimately would give us total bushels. So, and again, the key issue there in that is that we're given a rate function, bushels per year versus years, so ultimately the area under the curve is going to be the multiplication of those two units, in which will give us total bushels. Now, one thing to note that is if this is a positive valued function, then that's going to be just fine. We're going to get total bushels here. Now, if this were to be a negative valued function at any point during the interval, then we'd have to make an adjustment, kind of like what we did with displacement and total distance. Okay? But ultimately, if we're given that rate function C of t, then our integral, and again going from 1970 to 1980 would be the first 10 years, if you will, then the answer to the question is simply going to be that integral. Okay? Because ultimately each rectangle is going to be measured in bushels, and how do we accumulate the area of all the rectangles? Well, that's a definite integral. So with that said, if you look at page 369, there's another one that's very similar. The one problem that we have in this example 6, though, is that the rate function that we're given is in a discrete form, which means that we're given points instead of a function. So if we want to set out to find the total gallons, if you will, because the function is in gallons per minute versus minutes, which means the area under the curve is what we're after. But with that said, if we have this rate function, we'll call it r of t dt, and we are going from 0 to 60, and the answer to this we can't find using our calculator or the fundamental theorem because we don't have r. Okay, r is given to us in a table form. So really our only option at this point would be to estimate the area under the curve. And keep in mind, when we have points, okay, we can estimate that area of the curve in several ways. Well, one being LRM, RM, or MRAM. So we could use any of those. We could use trapezoidal rule, or we could use Simpson's rule. We really essentially have 5 different ways we could estimate that. Now, most of the time when we're given a problem like that, where it is a data table problem, they're going to tell us what to use. They're going to tell us to use the trapezoidal rule or Simpson's rule or whatever. If they don't tell us, then I guess it's your choice. This particular example, the book chose to use the trapezoidal rule, so they went through the trapezoidal approximation and found that the answer was 3582.5. So, like I said, ultimately that's just an estimate because we're using trapezoidal rule. We could use any of the 5 essentially. Okay. Now there's one final application I want to look at here because, like I said, most of our integral as accumulator problems are very much like these problems. We're given a rate function, and we just need to recognize that the area under the curve is going to give us a total of something, and depending on whether it's about potato consumption or water pumped out of a tank or whatever the case may be, the problems are set up almost identically. So there is one other topic that I want to look at that is a science application, which is work. And if you've taken physics, you might have some experience with work. And ultimately the work done by a particular situation is going to be given by the formula work equals force times distance. Okay? Now, like normal, if I have a force equation that is constant, if I have a constant force, then I have work over a certain distance, force over a certain distance, I should say. Then the area under the curve is going to give me my work. So I'm going to do force times distance. And depending on what the units are here, force could be measured in newtons, and distance could be measured in meters. And when we multiply a force times a distance, we get Newton meters, which is a legitimate unit for work done. Okay. There's others besides newtons and meters. We could do pounds and feet, or another one, and we usually generally call that work foot-pounds. So those are some common ones that we see in physics. But bottom line is here, we're going to calculate the work done. We're just going to do force times distance. And again, this is going to be used ultimately if we have a constant force. And the question though is, what if we have a variable force? If we have a variable force, then we're going to need to find area under the curve in a calculus sort of way, which means that if it's a linear, we could use a triangle, or if it's or a trapezoid, depending on what the interval is. Or we could just use our knowledge of integrals. No matter what the force equation is, we can find the area under it because we know how to find such areas no matter what the function is. I shouldn't say no matter what because we can't solve all integrals at this point, but most. So bottom line here is that we're going to look at work instead of in a constant setting here, which of course is the easiest case scenario. We're going to look at it in terms of using springs. And when we deal with springs, there's a law in science called Hooke's law that tells us that the force is equal to kx. So ultimately, k being some constant, we call that the spring constant. So it depends on how springy or not springy the spring is, if you will. And x is the distance. So ultimately, it's going to take a certain amount of force, okay, to either stretch or to compress the spring. And again, all of it's going to be based on what we call this Hooke's law. So if you look at your page 370, we have a scenario posed to us that says it takes a force of 10 newtons to stretch a spring 2 meters beyond its natural length. So ultimately what that allows us to do, that information, is it takes us 10 newtons and our distance is 2, and so that means that 5 would be our spring constant. So for this particular spring and this particular spring only, the force equation is 5x. So we'll find k by using the information given. And then ultimately here, the next part is how much work is done in stretching the spring 4 meters beyond its natural length. Okay? So ultimately, the work done is going to be the following. When we have a variable force here, okay, kind of like what we have here, we're going to look for the area under this curve. Now we can do it, of course, with a triangle at this point because we have our 5x is going to be linear. But in general, let's generalize it and say that work done is going to be the integral from a to b of whatever the force equation is, dx. Okay. So if we have a variable force, okay, then our integral is going to be found by summing up the area under the curve, the force curve, if you will, which is this. Very similar to what we had up here. This work done was found by finding the area under the force curve. And in the case of a constant, of course, that's just force times distance. Now, in the case of a non-constant, then we'll use our integral. Now, like I said earlier, since this is a linear function, we could theoretically just draw a picture and make a triangle and calculate that. But in general, if we generalize it, we can generalize it to any function, whether it's linear or not, by writing down this equation. So this is going to be our work equation. So we find work by, again, finding the area under the force curve from interval a to b, whatever that case may be. So in our case, we want to know how much work is done if we stretch the spring from 0 to 4. And our spring equation is 5x, our force equation, I should say. And if we differentiate, we get 5x squared over 2 on 0 to 4. And if we put a 4 in there, we get 80 over 2. So we get 40 minus 0 in there, give us 0. And so ultimately we get 40. And keep in mind that the force being measured in newtons, the distance being measured in meters, our units here would be newton meters. Okay. All right, so as stated, this technique using Hooke's law can be used for any spring equation as long as we can figure out the spring constant, which we're generally given enough information to do so. If we can write a force equation, then calculating the work done would be given by our integral here. Keep in mind that in this particular instance, we did the work done going from the spring being in its natural state to 4 meters beyond its natural length. We could have figured out the work done to get it to go from 2 to 4, which means it was already at 2. To go 2 further would be to go from 2 to 4. And if we did that, we would get, again, another integral. We'd have just had 2 in there, and we'd gotten a different answer. But regardless, the A and B here, the upper and lower limits, are going to tell us, where we're stretching the spring from and to, if you will. So with that said, the homework assignment that you have here is just going to be working with velocity, distance, acceleration, and so on, total distance, displacement, if you will, and then also some applications that where we're dealing with accumulation, which similar to the potato consumption, or the draining of the tank or filling of the tank, whatever the case may be, and then also some information regarding this idea of hook slot. So with that, I say good luck and enjoy.